So I have some lecture notes I'll put online from the CSSQI summer school I did last year. I think it was a 3-hour lecture, so I have to fit this all in an hour and a half. And it's about, so I just thought we'd finish by talking about entanglement in many-body systems. It's more like of a modern, I guess, topic that some of us are working on. And I'll explain what I think measures of entanglement tell you something interesting about many-body systems, and what exactly that sort of knowledge is. I consider sort of entanglement complementary to like two-point correlation functions or Green's functions or something like that you might look at in conventional sort of condensed matter measurements. One nice thing about entanglement is it sort of unifies condensed matter with quantum information with things like ADS, CFD, and gravity and stuff like that. It's sort of at the heart of this ADS, CFD correspondence for strongly correlated systems, which describes a duality or correspondence between some types of phase transitions and geometric theories of gravity. Like a Green's function or some correlation function that's based on 2 points of the system, you can learn something about locality and correlations using entanglement, but it's something different. You learn different things about how correlations characterize the system and so on. I'll see. I use language twice. Bad. Not changing it now. Correlations in, I don't know, systems. I don't know what I'm trying to say. So it's a way of understanding non-locality and which correlations are local, which are non-local. And also tells you something about which quantum systems are sort of fundamentally hard to solve. It can give you insight into which systems can be solved, which many-body interacting quantum systems might be able to be solved on, say, a classical computer. What's the complexity classes associated with different types of problems, and so on. So we've mostly been sort of, we've been talking about how basically Green's functions unify, unify language across many fields, maybe, or correlation functions or something like that. And we're talking about, lattice-based systems. We've also looked at sort of continuum field theories that come from high energy. So we've seen a lot of correspondences. And I think what entanglement does is it sort of brings this sort of correspondence to light in many other fields. So in order to talk about entanglement, you have to quantify, I guess, roughly what we're looking at. So all entanglement deals with a bipartition. So imagine taking a pure quantum system, a pure state, and dividing it into two different subregions. A and its complement B. That bipartition can be spatial. There's going to be a blob of some 10 to the 23 electrons, and you take out, I don't know, 10 to the 22 of them or something like that. That can be your bipartition. It could be in other modes. It could be across momentum states in the system, particle number in itinerant systems. But we'll basically imagine a spatial bipartition for what we're doing today. So the Hilbert space Okay, so it's the product. There's a product Hilbert space. And so this is probably a review, but a pure state, this whole thing, A union B, it's entangled if and only if it cannot be written as a product vector. A product state. It's unentangled. So of course the classic example of being, not classic, not classical, classic, standard example of entanglement would be a singlet. So I'm choosing a spin system with some basis, down, up. But of course, entangled states can be much more complicated than just simple two spin systems, if you want to call it that. So sort of what I want to talk about today is how do I take this intuition, this entangled singlet, which can't be written as a product state, and how do I guess, translate that into a many-body system? What if I have many spins or many electrons? How does the entanglement behave? And what does it tell us about the correlations? So this is probably a review, but just let me say a few technical things about how we quantify entanglement.
So is it like multi-partite entanglement?
It can be anything. So a many-body entangled system is all types of entanglement. Yeah. But it'll base certain, there might be monogamy theorems, right? So if you have two particles that are highly entangled, that particle can't be entangled with something else in addition in a large way. So all the usual, so you don't know what the entanglement necessarily looks like. What does that even mean? That's part of the problem, but in general, you can have all types of entanglement. So just let me remind you of the Schmidt decomposition. On this product Hilbert space, the idea is that there's just states that are existing on each side of that Hilbert space, A and B, and we can decompose the wave function into those states. So some orthonormal states, oops, I'll call them I. Such that the wave function of the entire pure system, A union B, I just won't label that. So those lambdas are Schmidt coefficients. You have to sum of the squares, I think. So to unity. Lambda squared equals 1. And the rank is the number of non-zero Schmidt coefficients in this sum. So if you have one element of that sum, then you're in a product state. And if you have more than one element in that sum, you're in sort of the generalized sort of entangled state. Schmidt rank, number of non-zero coefficients in the sum. Let me call it R, I don't know. You can call the case with one, the product case with one Schmidt coefficient to be classical in some sense. Greater than 1, it's entangled. So we're going to use these eigenvalues, or these lambdas, these Schmidt coefficients, to describe or to think about entanglement in many-body states. Let me keep going. So this is a Schmidt decomposition. You probably know what a reduced density matrix is. So again, it's a density matrix that's defined by tracing out the degrees of freedom associated with one of these bipartitions. So we start with the density matrix. Let me just define it as basically just the outer product. So if I have an ensemble of n possible pure states, then that I runs from 1 to n, and let's see, this row has to be equal to 1. Right, so then that's an operator. It's a matrix. If I trace out degrees of freedom just associated with, like imagine writing the wave function with the Schmidt decomposition, tracing out degrees of freedom, so taking a trace over just say region A or B, I get the reduced density matrix, which is also an operator. Which also operates on that product Hilbert space. So let me trace out B, the density matrix. This gives an operator acting on H only. On the Hilbert space for A. So the density matrix operates on the Hilbert space A, B. And the reduced density matrix is a convenient object for defining entanglement measures. I don't know what else to call them. Okay, so we want some way of quantifying this type of entanglement, if generalized maybe to the many-body case with a very complicated Schmidt decomposition and so on. So this is what we're going to use. And we can, in quantum information, there's millions of different ways to, maybe that's an exaggeration. There's many different ways to quantify entanglement. Somewhat, I might call natural for physical applications, like what we're doing, and some what you might call, I guess, operational for sort of like quantum information processing applications. So I'm more interested in something that's physically natural. Something that quantifies entanglement as a non-negative number that's 0 if the entanglement's 0. I don't know why I'm calling it E, entanglement, I guess. if you're in a product state. There's many different properties that you might want. If you have independent singlets, say, in a system, we can imagine making a quantum many-body system by just tiling a lattice with a whole bunch of singlets. So somehow you want the entanglement measure of independent singlets to be additive. You want it to be conserved under local unitaries, all sorts of other stuff. I'll quit writing these. Let me just say, compare these to operational measures. Operational measures of entanglement basically ask whether or not, if a system's entangled, whether it gives you some advantage or makes some task possible in quantum information processing that's not possible if you're unentangled. Like entanglement of formation. Or distillable entanglement. So these types of things tell you, if you have say a many-body system that's entangled, could be something like a quantum fluid or whatever, how much of that entanglement that occurs in that quantum fluid can be transferred to registers useful for quantum information processing tasks? It's sort of a different question than we're looking at. Okay, but if you're used to quantum information, then you're used to thinking about operational measures more. So the E that I'm going to use, the measure, is the entanglement entropy, which has nice analogies with the thermodynamic entropy. And so from a stat mech point of view, quantum stat mech point of view, it's actually quite natural to use. So we're going to use something called the Renyi entropy. It's an entanglement entropy that has a sort of generalized index or parameter. And you're used to seeing Renyi entropy. And the limit when this index, just some arbitrary number that can vary between 0 and infinity, is equal to 1. Von Neumann. So if you take the L'Hopital limit of this expression for alpha equals 1, you get the von Neumann entropy. If you work at my field, you'll see the second Renyi entropy a lot for alpha equals 2. And the big reason I mention the different Renyi entropies is you can imagine doing some sort of experiment or some sort of calculation on sort of small quantum systems or devices that you can do full tomography on to get the reduced density matrix. So quite often, this is what people will do to calculate the entanglement entropies. It's as complex as doing a diagonalization. It requires knowledge of the Hilbert space to the same amount. These integer Renyi entropies for alpha equals 2, 3, 4 can actually be expressed as expectation values of operators. Of some weird operators in a multi-sheeted path integral, which I won't talk about. But if you change the topology of your d+1 dimensional Euclidean path integral, you can write second and third and fourth Renyi entropies as with a stat-mech expression dependent on that path integral, which you can't do for the non-integer greater than 1 Renyi entropies. So therefore, these things are actually quite useful in many-body quantum physics. They can even be measured experimentally. Rajabul Islam, who just interviewed at IQC, did a second Renyi measurement on the cold atom system at Harvard like a couple months ago, basically. So I can tell you more about that later. But you should think of the Renyi entropies as just essentially obeying the same behavior in many-body systems as the von Neumann entropy. Harsh. These things have inequalities. The CS1's always greater than or equal to S2, and so on. So Sn also is greater or equal to Sm. This is for n less than m. And for alpha not equals 1, there's no strong subadditivity. Just a few things to be aware of if you see the Renyi entropies floating around out there. So how do these entropies quantify entanglement? Oh, I can give an example. Actually, one thing I want to say before that, just as a note. When you calculate the entropies, which you're doing on your computational project, right? So let's see. What I'm doing is really taking the trace, right? So I have a trace over, where's my reduced density matrix? Right, I have a trace over B, already in the definition of the reduced density matrix. So I have essentially an additional trace to do when I do the calculation of the full entropy to turn this thing into a scalar. So if I define the eigenstates of the reduced density matrix as, I don't know, W's, the set of all W's in the entropies are just written in terms of, I'll say D for some dimension. Etc. You're just writing the traces as essentially sums over the eigenvalues of the reduced density matrix. So once you have a reduced density matrix expression, diagonalizing it gives you access to the entropies. These expressions are nice because you can see certain properties of the entanglement entropy based on the eigenvalues. So if you only have one eigenvalue for the reduced density matrix, then the entropy will become 0. This is the minimum entropy case. So all the S alphas actually become 0. So it's like the unentangled case, right? So the case of one eigenvalue gives you a minimum. The maximum occurs when you have d eigenvalues all with the same value, 1 over d. So it's like a probability, the eigenvalues are related to a probability of being in these entangled states. I'm going to use these bounds. If I have time, I'll calculate the topological entanglement entropy for the toric code from this. What did I say? Properties? All right, so that's case 1. That's minimally entangled. So we have d cases of 1 over d for all the eigenvalues. This is a set. So you get some expression that's like, oh, 1 over d, 1 over d, to what? The alpha, right? 1 over d to the alpha. Okay, I'm writing out too many steps. Log d is what you'll get out of this. So that's the maximum case, sort of maximal entangled. So your entanglement entropy obeys this property that you wanted in a measure. S alpha rho A log D. Okay, so if you write the reduced density matrix with the Schmidt decomposition, then that D is just the rank of the Schmidt decomposition. There's probably an easier way to say that. But. Oops. Let me call it. Schmidt rank, what did I call it? R is going to be equal to the rank of the reduced density matrix. Okay, so it gives you another way of sort of basically thinking about entanglement. So let me look at a simple, I won't work it out in detail, but a simple example of a two-body case. You can just plug it into Mathematica and plot it in about 20 seconds. But if you calculate, I think it's kind of instructive. If you calculate the entanglement entropy for this wave function for 2 spins, so it's a product state. Oh no, sorry, I want an entangled state when, let's see, theta is, when the coefficient of these are both non-trivial, let's say, so sine theta. So theta is just some parameter that I'm going to vary. So it's a 2-spin system. My region A is one of the spins. My region, color red and blue if you want, red and blue, whatever. Theta is just a parameter that allows me to keep this thing normalized while I vary the entanglement in the system. And you can see that you have a product state, say when okay, so say when theta is 0, right, because the second term is 0. And if you have something like pi by 4 or minus pi by 4, you get a singlet. And you can vary this entanglement for all theta in between those two limits. So calculate the reduced density matrix. I won't do it all, but if you trace out the degrees of freedom associated with B, you get a reduced density matrix just defined on the Hilbert space associated with the states of A, region A. So you can figure out the eigenvalues, blah, 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 and then calculate all the different entropies as a function of what I call theta. And I don't know, they'll look something like this. They'll be periodic. And pi by 2, I guess. This is pi by 4. The maximum will be log 2. And the minimum will be 0. And if you calculate, say, the second Renyi entropy, what you'll find is the min and the max correspond, as you see in these formulas, if you just plug in any alpha. But quite generally, you'll get a curve that looks like this. And if you go all the way up to S infinity, I think you get something like this. Oops, infinity. So this inequality here is always obeyed, even in this very simple system. So what I want to do is sort of take this intuition and ask, how does it translate to many-body systems? Okay, the intuition that these 3 lines of this example gave you, but using these tools that that we've developed, or this measure that we've developed. Let's just remember a few points about classical entropies, or classical statistical mechanics. One thing you should be thinking of in light of this class, even though I won't teach it, is what does entanglement entropy mean if you have a field theory that's just a D+1 classical stat mech problem? Like I alluded to here, you can still write at least the second Renyi entropy, or the third, fourth Renyi entropies, as, expectation values of some modified partition function, so some Euclidean space path integral that has some really strange topological properties. But that Euclidean space path integral is still, it's a classical object in some sense. So classical entropies come to play in our intuition. Imagine I have an Ising model. So maybe I have a Hamiltonian that could be 1D, or doesn't matter what the dimension of the lattice is. If I define a Shannon entropy, depends what ensemble you're in. If you're microcanonical, what is it? Your entropy is just log of the number of microstates accessible to the system. If you're grand canonical, you have a Shannon entropy that looks just like your von Neumann entropy. All right, so I can call it 1. But now instead of reduced density matrices, I don't have a bipartition in the system. I just have classical probabilities of states in my state space. And if I looked at infinite temperature, I guess you already know this from the entropy of the Z2 gauge theory. We already looked at these arguments. So at infinite temperature, all states are equally likely. These probabilities, they're like Boltzmann probabilities that we just give you 1 over 2 to the n. All right, so your S1, plug that in, just get n log 2. It's extensive. If you put Boltzmann constant in front of that, that's your actual thermodynamic entropy that you measure by integrating the specific heat, right? If you don't have it in front of there, it's like a Shannon entropy. It's an entropy of information. It's telling you something about the ensemble. If you had 0 temperature, you know that you have a spontaneous symmetry breaking into 2 states. So it depends if you're in a thermodynamic limit or not, blah, blah, blah. But your entropy is either 0 or log 2. All right, so you just do log of the number of microstates. Like, for example, you could have log 2, just a constant. That's the third law, in some sense. There's a third law of thermodynamics that says that you cross over between this high temperature behavior that's extensive to something that's not extensive, essentially. And in some sense, that intuition translates into these entanglement entropies in many-body stat mech systems. So you could ask, what if this is a quantum Ising model? Transverse field Ising model. Now you're not looking at entropies of the ground state or something like that. You have a unique ground state through quantum mechanics. So it's not this quantity you're looking at, it's this thing I just erased. You're bipartitioning the system now? Question?
Yeah, so when you say that the ground state is either this state or this other state,
yeah.
It looks like if you compute the point Neumann entropy for the linear combination of both, right? Because if you choose either of both, it's a product state. So I would expect to have at 0 temperature like 0 entropy, right?
Yeah, but this is 0 entropy. I mean, it's just a constant and 0 for entropy. I would argue is basically the same thing. But yeah. Because in the thermodynamic limit, the entropy per spin or something will be 0.
Okay, but then how do you deal with degeneracies? Like,
that's all this is. This just tells the value of the constant tells you the degeneracy through this number. The number of microstates that you access is the degeneracy. It's this thing here. Yeah.
okay.
Yeah. But so just think of going from extensivity, is that even a word, to non-extensive, whatever. From scaling as n in your entropy to scaling as a constant or something sub-extensive. So you can basically just say, well, what if I had a quantum case? Just put a transverse field. Maybe minus. Again, you want to bipartition the system and so on, but if you did this bipartition and you calculated the entanglement entropy of that model in general dimensions, again, you have 2 cases. high temperature, you see that the entanglement entropy goes as, let me think here. I'm going to say the length of that bipartition, L to the D. So this is some length. That's not the unit I want. I want the volume of the system. That's what I want. Length of a bipartition. So in this case would be 1D, and the volume would be 2D. So let me just write it as a non-universal constant times the volume. V could be n, the number of lattice sites in your system. And if I lower it, so this is supposed to be analogous to this, an extensive scaling. And if you went to t equals 0, and you can imagine why you get extensive scaling. It's because the entanglement entropy can also pick up contributions from thermal entropy. So basically you're seeing a lot of thermal mixing in your state. But at t equals 0, what happens is this is reduced to something non-extensive that's just scaling as the length of the bipartition. It's called the area law. Not to be confused with the area law, perimeter law, for the Wilson loop, in the Torah code.
Is that up to logarithms?
Pardon?
Is that up to logarithms?
Yeah, I'll talk about that.
Okay.
So it's up to a whole bunch of stuff. Like laws, it's meant to be broken, so it's broken constantly. So this is just kind of the general, this is just what I would call the equivalent of the third law. And like a law, like I said, there's lots of exceptions to it. It's like you're going from extensive to sub-extensive. I'm going to talk about exceptions. It depends on exactly what type of quantum species you have, what types of interactions you have. But generally, this is the sort of paradigm with which you're operating in quantum mechanics, is that you have some sort of sub-extensive boundary law scaling at 0 temperature. So how do you see this? So there's no proof of this. Like I say, it's broken in some cases. But it makes sense sort of heuristically if you think of what the properties of many-body ground states look like from all your work in this class. Maybe it's best to look at examples. Start with 1D. Let me make a quantum mechanical ground state in 1D and 2D. Let me just make it by taking singlets, like I mentioned, just two entangled singlet states. Say this object here, and then putting it on lattices in different dimensions. So for example, in 1D, I can imagine a cartoon picture for a ground state that just looks like this, 1/2, down minus down up. Or it might have fluctuations, might be a superposition. This is actually a real ground state of a Hamiltonian, which is easy to solve, but I won't do it. A so-called AKLT Hamiltonian. just write it. It's a spin chain, S dot S. It's like a Heisenberg model. Plus a different term. That's the couplings squared. Interaction squared. It doesn't matter. You can write in terms of projectors onto some symmetrized spin 0. This is actually spin 1. You can write it as in some spin 0 basis that's spin symmetrized and show how you can get these, or sorry, spin 1/2. So you can get these spin 1/2 singlets populating a lattice like that. So let's just assume this thing exists. And the entanglement properties are just such that if you bipartition this system, you can imagine it's either periodic, right, or it could be an open boundary system. But there's no way to cut this system that gives you more than, say, 1 or 2 or 0 singlets. So imagine the left's your region A, the right's your region B. The best you're doing here is a constant. So for all the S alphas, somehow they're going to be proportional to log 2 or some constant. And that's just the simplest area law. It just means that your entanglement entropy is going like the boundary, which is 0-dimensional. It's called the area law because actually Raphael Sorkin was the first to calculate it in a system of quantum harmonic oscillators in 3 dimensions. So you cut out like maybe a spherical bipartition, and you look at the entanglement entropy of that sort of system of bosons, and you get an area law out, the area of the surface of the bipartition. So there was speculation back then that this had some relationship to this Bekenstein-Hawking entropy for a black hole, which is just the area law divided by Newton's constant or something. It's like the area law in the area of the black hole in units of Planck length or something like that. And so that intuition, I think, became much more concrete with the advent of the ADS-CFT. But it was calculated first, essentially numerically in boson systems. Or maybe Strednicki was numeric and Raphael Sorkin was analytical. But it's a good paper. You look it up. It's from maybe the 80s. You can basically calculate you can do this for an assignment in this class. 2D, the same intuition holds. I could take a 2-dimensional square lattice, populate it with singlets in some symmetry broken pattern. Something like that. And if my entanglement bipartition was, say this, A, everything else B, then my entanglement would be proportional to the number of singlets. So in this case, it'd be like 6 log 2, maybe, something like that. And if I increased the size of this bipartition by 2 lattice spacings, 1 on each side, then I increase the amount of entanglement by that same number, 2. Whereas if I draw my bipartition like this and done the same game, I have all these internal singlets in here, which don't cross the boundary, so they don't contribute to my entanglement entropy between A and B. And so by doing that increase of the area, or the entangled region, I still just get something that increases proportional to the length. So then this thing just goes as, say L, the length of the boundary. So the coefficient, incidentally, is something non-universal. In this case, it's some constant, and that constant's measured in units of the lattice length scale, say delta. Or in your field theory, if you imagine putting your field theory on a lattice, it's the UV regulator or the UV cutoff in the theory. Okay, so it's more like you'll get the, the leading order behavior tells you something about the range of correlations in your system, but it's difficult to get any sort of universal constants out of this leading order piece. Anything that could characterize the phase in some more specific way. That's just some examples. So generally, you can argue for the existence of the area law just by looking at your green function calculation. Say in the simplest case, when you have a mass in your theory. So if you have a gap, think of your Gaussian theory with a mass. And remember, your correlation function decays exponentially. And that exponential envelope allows you to define a correlation length. And that's finite, right? So that finite correlation length, if you translate it into the many-body entanglement arena, just gives you some sort of intuition for this area law. So a gap local Hamiltonian. Local has some specific meaning, but it just means that you don't have infinite range interactions. And it's gap, so it would give you a mass in your field theory. So you just imagine a Gaussian field theory, but it's quite generally true. You can define a characteristic length scale. Gap local Hamiltonian characteristic length scale exists. So I don't know, sigma z, site at position r, e to the minus r over, forget what that thing's called, correlation length. Right, so if that thing's finite, that's the, I'm scaling, this is kind of a UV type picture here. But if I was in a field theory in the continuum, or a many-body system, where my regions are of thermodynamic size, and the sort of long wavelength behavior, the long length scale behavior, it's just governed by that length. That is the length scale, right? So these localized correlations, you can imagine just entangling a region around the boundary within that correlation length. So if I have my region A and B, and my correlation length was just some length, that long on the chalkboard, then I just go that long around all my region, And at some point, when I scale this to the thermodynamic limit, the length scale of my region gets larger than the correlation length. And I'll cross over from basically a volume type scaling, where everything on the inside is entangled with everything on the outside, to an area law. So another way to think about it is that in that singlet picture, is that when you have a region A and B, your singlets are predominantly crossing the boundary near the edge, and in the center, the singlets mostly stay within the region somehow.
Roger, does this picture depend on the entanglement being singlets? Because it's hard to see Like if you had entanglement of like 4 lattice sites, then you would get additions to the entanglement from both axes.
Yeah.
But then why would it still switch to area instead of this kind of volume?
So just generally, it doesn't matter on the entanglement. It doesn't matter if it's singlets, sorry. If you have any type of gap local Hamiltonian, it just found that this area law is true.
But
So
it's
there's no
hard to
proof.
see, right?
It's definitely hard to see. I'd say it's non-intuitive, actually. You would expect a volume law, I think.
Yeah.
If you were highly entangled, you would expect a volume law. And the problem with this argument is if you take that correlation length to infinity, it actually breaks down. If you take that correlation length to infinity so that this picture breaks down, so you don't have local correlations anymore, you still get the area law. So you, with subleading corrections maybe, but you never get a volume law even if the correlation length is infinity. So if you tune to your quantum critical point and you measure the entanglement entropy, it's still area law in up to logarithmic corrections, say. I can actually maybe give you an argument for that, but okay, well let me just follow this up. So there's lots of different quantum systems is the problem, and they're not all gapped, Gaussian or massive Gaussian field theories or something like that. Although that's the simplest calculation. So it's worth asking sort of when this is obeyed. That's a question mark. I think harmonic. Coupled harmonic oscillators in d dimensions. That's a good calculation to look up. Sorkin and Mark Schmidt. Nikki, maybe? It's the kind of calculation you can just, I think after a class like this, you can look at and sort of just do. So it's the first calculation done in a many-body system, but generally any sort of free bosons or free boson field theory, just a free boson field theory discretized on a lattice, say. So free or even interacting. Careful if you put on a temperature, because you mix in thermal fluctuations, you'll get a volume law just from the thermal fluctuations. You need something like a negativity like a logarithmic negativity to cancel off thermal fluctuations. And any sort of, so we did path integrals for bosons, we did path integrals for spins and fermions. So basically any non-critical spin system. Same goes for bosons. If you can tune your bosons to a critical point, things are more complicated. But spins and bosons basically obey the area law up to a constant, very, very strictly. I'll say that because that constant's important. Famous violations are critical systems that are typically additive violations in d greater than 1. And they're multiplicative, I guess they're additive logarithms in d equals 1, 2, so I'll just say additive. So you don't get a volume law even when you violate this argument of locality or of length scale. Additive functions, topological order. Topological order is the toric code. You have an additive constant, which maybe I'll calculate. Maybe. And I think the most important one is fermions. Anything with a Fermi surface, to be specific. Not Dirac fermions where you have a Dirac cone. But fermions, you have a multiplicative log. And this is a pretty fun violation. Actually, Guy is an expert in this, and I heard he's teaching this right now in Psi. So look up his lectures. So the most important violation, I see anything with a Fermi surface, you get something that's like log, L log L, say in 2 dimensions. Let me just mention critical systems. Why do critical systems violate the area law only additively? It's really easy to get a critical system in 1 dimension. You can like either tune your transit field Ising model to the critical point, or you can just look at the 1-dimensional spin 1/2 Heisenberg model or something like that. H over J equals 1. As I argued in a very simple context for the free propagator in a massless theory, you don't have the definition of a length scale anymore. So compared to massless, phi-4 theory, or massless Gaussian, the correlation length goes to infinity. Basically, just the propagator doesn't have this form anymore when you do this calculation. We look at this more in 705. But there's no length scale anymore. So that picture of singlets doesn't really apply anymore. So you can say, well, what replaces? Maybe there's some UV singlet type physics. So what replaces this long wavelength area law? So sort of the heuristic way to see how this looks is imagine dividing your system into region A and B. I'm going to, as an ansatz, I guess, demand that you get some sort of order 1 entanglement at every length scale. I just realized I'm saying every length scale in a renormalization group sense. So this doesn't mean anything to you guys, but I'm doing it anyway because I started. So imagine I have a singlet. Maybe I have to think of my monotonicity theorems for entanglement if I'm going to do this argument. But whatever that number is, might not be log 2. Just imagine it occurs equally well at every length scale. Because if it was favored at some length scale in the system, then this wouldn't be true anymore. The idea that you don't have a length scale. So if I start in the lattice length scale, oh, I totally did that wrong. There's no entanglement. Imagine that I have, something like this. I'm cutting a singlet there. So if we get that order 1, which may or may not be log 2 or something like that, times 1 singlet at that length scale. But this is the part that doesn't make sense in this class. If I do an RG transformation to block spins, for those of you that have done the RG, I can define the next length scale by just combining the degrees of freedom of 2 neighboring sites into 1 big site called a block spin, as in block. Nothing sophisticated. And if I imagine I have 1 unit of entanglement occurring at that length scale, I add 1 to this. Now let me make another block spin that's bigger. Now I only have 2 spins in my system. I'm at the biggest RG length scale. I'm at the like IR. Again, only have 1. So if I add up all those 1s, I get 3. And what 3 is log base 2 of the number of sites. Because every time I did a block spin transformation, I took 2 sites into 1. Right? And there's 8 spins in the system total. So this is actually a log. So 3 is equal to log L. That's a great proof. So that's how you get. In the last question of your assignment, or your computational assignment, that's why you have that logarithmic scaling. So if you tune to the critical point, and you look at the entanglement entropy between 2 halves, or 2 parts of the system, you'll see that you'll get a logarithm. So it's more, more precisely. The entropy goes as something like C/3 log. In a finite size system, it's L/pi log sine. But that's just a finite size version of C/3 log L.
Is this working for large L? Like there's an additive constant as well.
Yeah, there's additive subleading pieces.
Okay.
So actually when you do, so what I'm having you do on the computational assignment is plot S versus X. X is the length of your bipartition. You get something like this. And actually if you plot it as, sine pi x over L, you'll get something that's like a straight line, folds back on itself. And if you look at the deviation of that thing from a straight line, it happens mostly down here. Oh, I drew it the wrong way. The deviation's biggest down here where you're closest to like the UV. I mean, you're probing lattice length scales. That's these additive constants here. So when you do a fit to extract the central charge, sees the slope. Basically, you'll see this part will be screwing you up. It'll give you something that bumps it off like whatever the value is supposed to be, 1 or 0.5 or whatever. So that's where the log comes from. It's this RG sort of argument that's only valid at criticality. If you're not at criticality, what happens is you just get an edge effect, and then this thing will flatten off to the area law, which is just 0-dimensional. What you see in higher dimensional critical systems, I won't do the counting. But I'll make you watch me draw this. One, two, three, four, five. Oh. Okay, I'm getting lazy. Imagine I do the same argument and I cut this thing in half into region A and B, but I have no length scale. I'm going to have order 1 at every length scale, and at the lowest length scale, I can imagine just having singlets like this, everywhere in the system. I'm cutting a value of L of them. So instead of 1, I get L, which is one of the linear sizes of the system. Then I got to do the block transformation, so I do it like this. And so on. So instead of having 8 objects entangled, I just have 4. That's L by 2. Do another block transformation. Did I do that right? Yeah. I would get 2, so that's L by 4. Keep going. This is L. This is like a geometric series, I think they call it. It just gives you another L. You get 2L out of that. So the area law is still obeyed in critical systems in 2 dimensions. And what happens is all the interesting stuff comes out as a subleading correction. all the universal physics, all the, so that suppose, that violation, actually both of these violations are sort of very weak violations of the area law. So the only thing that really doesn't obey the area law is when you have a Fermi surface. And actually you can do a counting argument like this essentially in momentum space, and you can see exactly why you get L log L out. One way of thinking about it is like if you have a one-dimensional system that has the right central charge, and then you stack a bunch of these one-dimensional systems, you stack up L of them in one direction, then you get L times log L. I mean, it's basically the same type of counting argument. I think there's nothing too mysterious about that violation. Okay, so I'll do the topological thing last. So if I have a system in one dimension divided into A, 2 dimensions, I don't know, L by L, 3D, L by L by L. Just remember, if your Hamiltonian's gapped, I was using that for Hilbert space today. If your Hamiltonian's gapped versus critical, I'll say gapless here. There's two different cases. Well, I misaligned my table. But so this is just constant. This one will go as L, L squared, and so on. If you're gapless, you have a log in 1D. In 2D, you'll have area law unless you have a Fermi surface. Ask you Frey about that. Then you're going to have, L log L. That's this. And then in higher dimensions, you're going as L to the D minus 1. So L squared in 3 dimensions. And then Fermi surface. It's like your only violation. So it'll be L squared log L. So up to additive constants, that's everything we know about entanglement entropy, basically, for many body systems. So the additive constants, I could talk about that for like an entire 3 months because they're really interesting. In critical systems, the additive constants are what gives you universal numbers. In analogy to like the critical exponents, you might see a correlation like diverging with some critical exponent as you approach a phase transition. That critical exponent is universal. It doesn't depend on the lattice cutoff, generally, is what makes it universal. There's no UV pollution in the term. And that's what happens in your entanglement entropy. You get subleading pieces that are universal or have universal coefficients or universal functional, like scaling functional forms. And because they're universal, you can compare them between many different theories. You can do lattice calculations, you can do field theory calculations, and you can do this ADS CFT, where you have the metric in a 2-dimensional higher, like negatively curved space, and you're calculating the G of D6. And actually, if you do those calculations, you get exactly, especially in 1+1, where all the conformal transformations are known well, you get exactly this form from the gravity, and using Einstein gravity or something like that. So that's the kind of the power of universality and the power of entanglement entropy, is you can compare these numbers between different theories. So the simplest, I'd say important universal number doesn't come from critical systems. It comes from topologically ordered systems. It's called the topological entanglement entropy. So think back to the toric code. vertex, black hat. It's two stabilizers, sigma, sigma, sigma z, sigma z, sigma z, sigma z, sigma x, blah, 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 on the vertex. Remember I argued last time that the wave function is a superposition of loops. So if you look at the sigma z basis, you make a ground state by drawing loops. You make one contribution to the ground state by drawing closed loops. So the wave function is I'll call it a loop gas. I don't know, whatever your loops look like. Man, you know class is almost over when you start writing equations like that. So if you take this loop gas and you bipartition the system into A and B, you can ask, basically, what's the entanglement entropy of that ground state? Form the reduced density matrix. If you want, trace out a region A. Alyosha Hama was the first to do this. He's a longtime perimeter resident. He teaches psi sometimes now, I think. Hama. And Shalgun's famous for kind of generalizing this too. Shalgun and his collaborators, and Kitaev and Preskill. So imagine now I have a bipartition, and put that bipartition at the lattice length scale. Actually, you can bipartition it like that, or it could be topologically non-trivial too. Because the toric code you often think of as being on a torus, so either one of those works. And so if I look at that microscopic picture, and I sort of ponder what that loop gas means, it's really a constraint on the boundary of my region. I don't really want to draw this whole dual lattice thing, but imagine I have my lattice divided into I have my degrees of freedom, which sit on the bonds. And imagine I divide somehow my lattice into A's and B's, in a region A and B. So I'm kind of zooming in on that bipartition. I can say a loop gas, loop crosses the boundary. So there's a loop there somehow, drawing a closed loop. Well, I wasn't all that precise, but. So you can basically give the boundary, which is discretized, the same as a lattice, a value of +1 or -1 based whether or not that loop crosses the boundary. So here you might cross it twice, and there you might cross it twice. So these are some dual variables, but they're just Ising variables. So let me think in terms of those yellow bars. And now I have this big loop gas like this, and I've divided the region spatially somehow into region A and B. And so I'm quantifying how many loops cross that boundary. So it's kind of interesting. So we can use our intuition for the entropy. What does it mean for the entanglement entropies, S alphas? So let's use our intuition for the entropy. So this dual lattice boundary, which I guess is yellow there, has loops crossing it, which are all these spin ups in the toric code. All right, so let me just draw those as closed lines. And some cross the boundary and some don't. But other than this topological restriction on the loops, they're basically free to be any shape or size that you want. So you can imagine counting the number of states available to the boundary, the number of microstates just available to the boundary. It's like the way you calculated the classical entropy. You know, so if you had the Ising model in its ground state, you would log 2. If you had the Ising model at infinite temperature, you have log of 2 to the n, or something like that. Right, so on the boundary, you can imagine having the number of microstates at maximum would be 2, because each one of these dual variables is either 1 or 0, true or false, whatever, right? True, the loop's crossing the boundary. You know, false, the loop's crossing. So it's 2 to the size of that loop, 2 to the L. Because there's no other constraints visible with this loop gas. These things are just moving around. You have a superposition of them, maybe. You imagine this, it just looks like this thing with quantum fluctuations moving these loops. But there's one important constraint, and that's if you went around all these links, all those yellow links, and you kept track of how many ups and how many downs you have, you might not know how many exactly loops cross the boundary, but you'll know as you go around this boundary and you come to your last, you know, your very last link, maybe it's this one here, you'll know that if an even number or an odd number of loops crossed into the boundary, you have to have one more, because these things have to be closed loops. So there's a topological constraint. And so that gives you one bit of information in the sort of the Shannon sense. So it's 2 to the L minus 1 available microstates to a loop gas. And that minus 1 is specifically because of the loop structure. Okay, so if I took the classical entropy of that boundary, I would get L log 2 for the first contribution minus log 2. What does it mean quantum mechanically? That was just a classical, you know, one-dimensional lower boundary calculation. But remember the Schmidt rank. It's basically, no, the Schmidt decomposition is bound by this, so. Naive. Two L, oops, big L minus 1. IA, whatever your basis is, IB. And the reason is, because what the Schmidt rank's telling you is you sort of have freedom to choose how the loop structure looks inside, and you have freedom how it looks outside. And the Schmidt rank is all the possible ways that you match up the inside and the outside. Right? And they have to be matched up conditional on that, on the constraints in the loop gas in the wave function. So the entanglement entropy is actually less than or equal to this. And what I don't, I guess, now, thinking about it, know how to prove, is that when you actually include all the fluctuations in the superposition of the loop gas, is that this coefficient basically just gets, this thing's non-universal, like I told you. It has to depend on the lattice length scale physics. So this thing can't be precisely what you get. So you just get some, this should be small, this should be big L, some constant times L. But this piece survives in the actual calculation. If you look at what Alyosha Hammett did. So what you really get is an area law. And you get this negative additive, negative constant. It's called the topological entanglement entropy. So I just think it's a nice example where the entanglement entropy tells you something very non-trivial about the type of ground state that you have. Anytime you see a log 2, you basically know that you have a Z2 gauge theory, and that 2 is related somehow to the discrete symmetry in the gauge theory.
Is this independent of the choice of the ground state when you have degeneracy? Like for instance in the choice, right?
Yeah, it's independent of the topological degeneracy. Yeah.
But I find that it's like hard to believe, because if I take any linear combination of the 4 ground states first, then I would expect that the entropy depends on the coefficients that I choose, right? So you know you have 4-dimensional ground states.
Right. So your ground state's a superposition of all states, regardless of which topological sector they basically lie in. And the coefficients of all the states are unity.
Right, okay.
So I think the idea of the topological degeneracy, I mean, it's just topological somehow. It's, the wave function still has, it's still a well-defined superposition of all possible loop states. They just happen to lie in 4 topological sectors. Okay. I think that's how I would look at it.
The thing is that you chose a very nice partition, which is I think this calculation is done when the bipartition is such that the subsystem A can be shrinked to a point, right? Right,
so these are actually different.
Right, so...
Yeah, this is topologically non-trivial. This one is. So in general, this is true, even in this case.
Okay.
But you have to be a little bit careful with that. Let me just... It depends on the anionic species you have or something like that. So
it also depends on the topology of your bipartition.
It does, yeah. But it's not much different. You just got to be a little bit careful of how much flux you have piercing that region. So, but in general, you could do this calculation numerically, sort of on a. You could do this in the classical system, or you could do it in the path integral. And calculate this type of topological entanglement entropy. I didn't say it, but this is independent of the Renyi index, this log 2. So you can do the second Renyi entropy for the toric code. You can get exactly this behavior out. Or you can look at more complicated topological order that's not exactly solvable. So Alyosha did sort of the exactly solvable case of the pure gauge theory. But this turns out to be generally true. This number tells you about the number of anyons, which I haven't talked about. So the emergent, the emergent quasi-particles that are gapped in your system, they can have different statistical properties. Anyons, they call them. That tells you something about that. So it's a very powerful concept, which is sort of born out of just this relatively simple state space counting. And I think this is the first example that people really studied in detail for corrections to the area law. So this Hamiltonian is actually gapped, as I told you. But even if it's gapped, you can have constants, additive constants that are useful. And in the critical case, this idea is just generalized very non-trivially. You have functions that depend on the aspect ratios and all the sort of topological properties of your subregions. And like I say, I could lecture about that for an entire class. Maybe I'll invent that class and call it 734. But that's definitely something for a different time. All right, I guess that's all I have to say. None of this is on the exam, because there is no exam. But I hope at least I motivated. I hope at least I motivated why you're seeing a log for the last problem of your computational assignment. Okay, so thanks for good time.